不锈钢 Stainless Steel 生产流程。不锈钢生产流程。不锈钢因其优异的耐腐蚀性、耐高温性及强度，广泛应用于建筑、工业等领域。其生产过程繁复，从原料熔炼到最终成品，每个阶段都至关重要。以下将带您深入了解不锈钢的生产流程。一、原料准备。主要原料：铁矿石、铬、镍等合金元素，其他添加物。为了达到不同等级的不锈钢特性，会添加钼、钛、铜等元素。二、熔炼。高温熔炼，将准备好的原料在高温电弧炉或氧气转炉中熔炼，使其成为液态钢。合金化，在熔炼过程中加入各种合金元素，以达到所需的成分比例。三、精炼。脱氧，为了去除钢液中的氧，加入脱氧剂如铝、硅等。成分调整，精确控制钢液中的成分，确保符合产品规格。不锈钢 Stainless Steel 生产流程。不锈钢生产流程。四、铸造。连铸法，将液态钢连续浇铸到水冷铜模中，形成钢坯。铸锭法，将液态钢浇铸到铸模中，冷却后形成钢锭。连铸：一、钢包；二、塞子；三、中间包；四、护罩、耐火砖套；五、结晶器；六、滚动支撑；七、转弯区；八、护罩；九、液位；十、半月板；11、提取单元；12、板坯。A、液态金属； B、固化金属； C、炉渣； D、水冷铜板； E、耐火材料。不锈钢 Stainless Steel 生产流程。五、热轧。加热，将钢坯加热到高温，使其具有可塑性。压制，将加热后的钢坯通过轧机，使其厚度减小，宽度增加。六、冷轧。冷轧，将热轧后的钢板在常温下进行压制，以获得更精确的厚度和更好的表面光洁度。七、热处理。退火，将冷轧后的钢板加热到一定温度，再缓慢冷却，以消除内应力，改善机械性能。淬火，将钢板快速加热到高温，再迅速冷却，以提高硬度。八、表面处理。酸洗，用酸溶液去除钢板表面的氧化物和杂质。抛光，对钢板进行抛光，使其表面光亮。九、成品检验。物理性能检验，检测钢板的强度、硬度、韧性等。化学成分检验，检测钢板的化学成分是否符合要求。表面检验，检测钢板的表面质量。十、切割成型。根据客户需求，将成品钢板切割成所需的尺寸，并进行折弯、冲压等成型加工。不锈钢的种类繁多，不同的等级和用途，其生产工艺也略有差异。不锈钢 Stainless Steel 生产流程。不锈钢热轧工艺流程。不锈钢热轧工艺是以板坯主要为连铸坯为原料，经加热后由粗轧机组及精压机组制成带钢，从精压最后一架轧机出来的热钢带通过层流冷却至设定温度，由卷取机卷成钢卷。冷却后的钢卷外表有氧化皮，呈现黑色，俗称不锈钢黑皮卷。经过退火酸洗，去掉氧化表面，即为不锈钢白皮卷。不锈钢市场流通的大部分热轧产品为不锈钢白皮卷。具体不锈钢热轧生产工艺流程如下。 不锈钢 Stainless Steel 生产流程，不锈钢钢板生产工艺流程图。不锈钢 Stainless Steel 生产流程，不锈钢冷轧工艺流程。在不锈钢热轧之后，部分不锈钢热轧品直接被下游使用，部分热轧产品需要继续加工成冷轧之后再使用。不锈钢冷轧多采用热轧厚度在 3.0 到 5.5 毫米厚度的不锈钢热轧产品，经过冷轧设备的压延加工之后，生产成不锈钢冷轧产品。当前不锈钢冷轧主要生产工艺为2类：不锈钢单机架冷轧、不锈钢多机架冷轧。具体生产流程如下图。不锈钢 Stainless Steel 生产流程，不锈钢热轧卷板生产工艺流程图。不锈钢 Stainless Steel 生产流程，远龙不锈钢。以上影音介绍说明仅代表个人观点，供大家学习交流，不代表公众意见。附件 YT video How is stainless steel made? How is made stainless bar and billet?
Is one of the most versatile and widely used materials in the modern world, playing a crucial role in industries ranging from construction and automotive to medical devices and kitchenware. Its unique properties, including resistance to corrosion, high strength, and a sleek appearance, make it indispensable in countless applications. But how is this wonder material made? The process of manufacturing stainless steel is a complex and fascinating journey that involves multiple stages, from the selection of raw materials to the final finishing touches. In this video, we'll take you through each step of the process, shedding light on the science and engineering that goes into creating this remarkable alloy. The story of stainless steel begins with the selection of the right raw materials. The primary component of stainless steel is iron, which is extracted from iron ore found in the Earth's crust. Iron ore is rich in iron oxides and must be refined to extract pure iron. This is done in a blast furnace, where the iron ore is heated to extremely high temperatures, around 1,700 degrees Celsius, along with coke, a form of carbon, and limestone. The intense heat causes the iron ore to melt, and the carbon from the coke reacts with the oxygen in the iron ore to form carbon dioxide, leaving behind molten iron. This molten iron, also known as pig iron, is the starting point for making stainless steel. However, stainless steel is much more than just iron. Its defining characteristic is its resistance to rust and corrosion, which is achieved by adding specific alloying elements, most notably chromium. Chromium is essential because it reacts with oxygen to form a thin, invisible layer of chromium oxide on the surface of the steel. This oxide layer is what gives stainless steel its stainless property, as it prevents further oxidation and corrosion of the metal beneath. To achieve this, chromium is added to the molten iron in the form of ferrochrome, an alloy of iron and chromium. Typically, stainless steel contains at least 10.5% chromium by weight. although the exact percentage can vary depending on the grade of stainless steel being produced. The addition of chromium is just the beginning. Depending on the desired properties of the final product, other elements such as nickel, molybdenum, and manganese may also be added to the molten steel. Nickel, for example, enhances the corrosion resistance of stainless steel and gives it a more lustrous finish. Molybdenum increases the steel's resistance to pitting and crevice corrosion, which is especially important in environments with high chloride content, such as marine applications. Manganese improves the steel's strength and hardness. These alloying elements are carefully measured and added to the molten steel in precise quantities, as even small variations can significantly impact the properties of the final product. Once the alloying elements have been added and thoroughly mixed with the molten iron, the next step is to remove any impurities that might have been introduced during the process. This is done through a process known as argon-oxygen decarburization, AOD. In AOD, a mixture of argon and oxygen is injected into the molten steel. The oxygen reacts with carbon and other impurities to form gases that can be removed, while the argon helps control the temperature and prevent excessive oxidation of the chromium. The result is a purer form of stainless steel, with a carefully controlled composition that ensures the desired properties are achieved. After the AOD process, the molten stainless steel is ready to be cast into solid form. This is typically done using a method called continuous casting, where the molten steel is poured into a water-cooled mold. As the steel cools, it solidifies into a long continuous slab or billet, which can then be cut into smaller sections as needed. Continuous casting is preferred because it allows for the production of large quantities of stainless steel with consistent quality. The slabs or billets are then allowed to cool further before being sent to the next stage of the manufacturing process. The next step in the production of stainless steel is hot rolling. The cooled slabs or billets are reheated to a temperature of around 1,200 degrees Celsius and pass through a series of rollers. These rollers apply pressure to the steel, gradually reducing its thickness and shaping it into the desired form. Hot rolling not only shapes the steel, but also improves its mechanical properties by refining the grain structure. The steel can be rolled into various forms, such as sheets, plates, bars, or wires, depending on the intended application. After hot rolling, the steel is allowed to cool down again before moving on to further processing. At this point, the stainless steel still has a rough, oxidized surface that needs to be cleaned and finished. This is where the process of pickling comes in. Pickling involves immersing the steel in an acid bath, usually a mixture of hydrochloric acid and nitric acid. The acid removes the oxide scale and any other surface impurities, leaving behind a clean, smooth surface. In some cases, additional treatments such as electropolishing may be used to achieve an even higher level of surface finish, particularly for applications where aesthetics are important, such as in kitchenware or architectural components. Once the stainless steel has been pickled and cleaned, it is ready for the final finishing processes. These processes vary depending on the intended use of the steel and can include cold rolling, annealing, and surface finishing. Cold rolling involves passing the steel through rollers at room temperature to achieve a precise thickness and improve its surface finish. Annealing is a heat treatment process that relieves internal stresses in the steel, making it easier to work with and enhancing its ductility. Surface finishing can involve a variety of techniques, such as brushing, grinding, or polishing, to achieve the desired texture and appearance. The final product may have a mirror-like shine, a matte finish, or a textured surface, depending on the customer's specifications. The production of stainless steel doesn't end with the final finishing. Quality control is a critical aspect of the manufacturing process, ensuring that the steel meets the required standards for strength, corrosion resistance, and other properties. Samples of the steel are taken at various stages of production and subjected to rigorous testing, including chemical analysis, mechanical testing, and microstructural examination. These tests verify that the composition and properties of the steel are within the specified limits, and that there are no defects that could compromise its performance. Only after passing these tests is the stainless steel considered ready for use. Stainless steel is then ready to be shipped to manufacturers who will transform it into the products we use every day. It could become part of a kitchen appliance, a piece of medical equipment, a structural component in a building, or even a piece of jewelry. The versatility of stainless steel is one of its greatest strengths, and its journey from raw materials to finished product is a testament to the ingenuity and precision of modern metallurgy. The production of stainless steel is a complex and highly controlled process that requires expertise in both materials science and engineering. From the selection of raw materials to the final finishing touches, each step is carefully designed to ensure that the steel possesses the properties needed for its intended use. Whether it's the chromium that provides corrosion resistance, the nickel that enhances durability, or the precision rolling that achieves the perfect thickness, every aspect of the process contributes to the creation of a material that is both strong and beautiful. So the next time you see a shiny piece of stainless steel, take a moment to appreciate the intricate and fascinating journey it has taken to reach you.
At Sandvik, manufacturing's based on recycled steel and alloy materials. We buy recycled steel only from certified suppliers. The raw materials analyzed and controlled, and any harmful ingredients are removed. The recycled steel is melted at 1600 degrees centigrade in an electric arc furnace. In the argon-oxygen decarburization vessel, carbon content is reduced to stainless steel levels. Exhaust gases from the furnaces and AOD processes are filtered to cut pollution, and the dust thus extracted is further processed for metal recovery. The melt is transferred to a ladle furnace for fine-tuning of temperature and chemical composition. The chemical composition of the melt is closely monitored throughout the process, and we make continuous analyses to guarantee the correct steel grade and ensure traceability and consistency between the batches. The results are entered in a certificate that accompanies each batch through every stage of the process. The continuous cast material or ingots are pre-rolled in a blooming mill and then transported to a heating furnace to be reheated to the correct rolling temperature. The blooming mill is integrated with Sandvik's modern rolling mill to form one continuous production line. The new mill provides quick product dimension changeover, short lead times, energy savings, and excellent product quality. Here, round and square billets and bars are rolled to a wide variety of sizes in many passes, and cut into requested lengths. To produce bars in heavier dimensions, the steel is cast into ingot molds by bottom pouring. Each ingot is marked with a heat number to ensure full traceability. The ingots are stripped from their molds heated and transported to hot working in an ingot rolling mill. The pre-rolled ingots are then heated to 1260 degrees centigrade to optimize further processing, after which they're transported to the computerized forging press. The hydraulic forging press, with its 1800-ton press force, is used to produce bars in sizes up to 450 millimeters. The bar, now round, is reheated to 1260 degrees centigrade in a quench annealing furnace, followed by rapid cooling in water to ensure the material structure is in accordance with official international and customers' specifications. The bars are transported to the cooling bed. Before being peel-turned and polished to mirror finish. The finished bar is ink-marked and visually inspected. The destructive testing stage includes tensile strength tests, impact tests, as well as confirmation of corrosion and microstructure properties. The bars are delivered together with the required material certification.